All right, we'll begin. Now, this is what we did in the last class, series source transformations. Okay, the idea of converting a voltage source with a series resistance to a current source with a parallel resistance. Okay, with a resistance in parallel and vice versa, back and forth. Okay, the idea, the whole logic was that if you look at the terminals, the terminal behavior from the perspective of A and B, okay, this voltage source with a series resistance is going to behave exactly same as a current source with a parallel resistance. This is what we discussed in the last class. And then we looked at the proof and saw that the current flowing in the load resistance is the same in both the top and the bottom circuit. They're equivalent. Okay. Then we did a couple of problems involving source transformations. Then we went into the very interesting idea of Thevenin and Norton equivalent circuit. Okay. The Thevenin and Norton equivalent circuit is all about circuit abstraction or circuit simplification. More than simplification, it's about abstraction. Meaning that if I have a complex circuit, if I have a complicated circuit, the idea of Thevenin equivalent is to come up with one voltage source with a resistance in series. That's behavior is exactly the same as far as these terminals are considered. Okay. So to the left of these terminals, A and B, the argument is that all of this circuit behaves exactly the same as all of this circuit. Okay, so that is the idea of Thevenin's equivalent, a voltage source in series with a resistance that behaves exactly similar to, in terms of the terminal behavior in all respects, to a benchmark circuit, to a circuit, the underlying representation, the underlying circuit. Okay, so that's the idea of Thevenin's equivalent, and the same with Norton's equivalent as well. For the Norton's equivalent, it is a current source with a series resistance. Okay, this is still R Thevenin. This is I Norton. This guy is V Thevenin, and this is R Thevenin. Okay, so one is the Norton equivalent, the other is the Thevenin equivalent. Okay, so that was the idea that we discussed in the last class. Now, how do we find the Thevenin equivalent? There are two steps to finding the Thevenin equivalent, right? When you go about finding the Thevenin equivalent of a circuit, the Thevenin equivalent is a voltage source in series with a resistance, right? So there are two things we have to find. We have to find the Thevenin's resistance first. Okay, that's the Thevenin's resistance. The first step or the second step, the order does not matter. The first step is to find the Thevenin's resistance. And when you're finding the Thevenin's resistance, what you do is you deactivate all independent sources. Okay, you deactivate all the independent sources. Okay, the second step, or the next step, is to find the Thevenin voltage. Okay, Thevenin voltage is defined as the open circuit voltage across the terminals A and B. What is the open circuit voltage? That's V Thevenin. What's the resistance looking in? That's the R Thevenin. This is what we discussed. Okay, we saw an example of this. Here. The open circuit voltage is when you keep the terminals A and B open circuit. Okay, what is the current flowing in this open circuit? What's the amount of current flowing through these open terminals?
0.
0, right? So using that observation, we calculate the value for the V Thevenin, and also the next step is to find out the R Thevenin. Okay, so this is what we do. This is what we discussed in the last class. Okay, so we found the value of V Thevenin to be 32 volts, and the value of R Thevenin is by deactivating the independent sources. So when you deactivate a voltage source, you short circuit it. When you deactivate current source, you open circuit. Okay, so that's the idea. So that is what we discussed in the last class. Then we went on to talk about another additional method, which is the test voltage, test current method. Of course, we saw the exact same procedure for Norton current. For Norton equivalent circuit, instead of finding the open circuit voltage, okay, we find the short circuit current. We short circuit these two terminals and find the current. Okay, so that's the exact thing that we did in the last class. And then we went on to solve some example problems. Okay, we went on to solve some example problems. Then we discussed this new technique of finding the Thevenin equivalent resistance using a test voltage or a test source. Okay, using a test voltage or a test source. So oftentimes in circuits like this, it is not very obvious, um, and it is not very straightforward to calculate the input resistance. Okay, even if I deactivate, the idea of deactivating an independent source is to replace it with a short, right? Even in this scenario, it's not easy for me to calculate the R in value. It's not easy for me to calculate the R in value. In order to do that, I deployed a very interesting new technique, which is to apply a test voltage and a test current. Okay, I apply a test voltage and a test current. Then, in order to find Rn, all I have to do is to get algebraic expressions for V test and I test and divide V test over I test. Okay, once I do that, and we'll look at a couple of examples in today's class. Today's class will mostly be about examples. Okay, so when we do that, we get an expression for I test and B test. Okay, and then eventually what we do is, once we have that expression for V test over I test, in order to get R Thevenin, we divide V test by I test. Okay, so that gave us a value for R Thevenin to be 100 ohms. Okay, so that's the idea that we discussed in the last class. We look at some examples today. So there are some more concepts: maximum power transfer theorem and superposition theorem. Okay, there are two more concepts that we need to discuss to finish this chapter. Okay, superposition theorem, which tells how to evaluate circuits that have multiple sources. We know different techniques for this. We know the node voltage, mesh current methods, and other methods for this. But um, in the presence of two independent voltage sources, how can I evaluate the behavior of one? How can I evaluate the behavior of the circuit or the response of the circuit separately, independently? The response of circuit to the voltage source, then the response of the circuit to the current source. Then if my circuit is linear, which in our case, all the circuits that we see in this class are linear, the argument is that we can add the two responses together. The independent response of the circuit to the voltage source and the independent response of the circuit to the current source. When we add them up together, we get the combined effect of both these sources. So that's the idea. We look at that later. And then we'll also look at the maximum power transfer theorem, and that has to do with impedance matching. Okay, but for now, what I want to do is to spend some more time on the example problems, on some example problems relating to this Thevenin's equivalent and Norton's equivalent. Okay, so questions so far, please. Okay, okay, let's look at some example problems. Okay, let's start with an easy one here. So I'm going to do this. I copied a few, let's see, problems. I have actually 4 problems planned out here. So let's start with this guy. I don't know. So I'm going to copy this. Okay, so paste it over here. We'll call this problem number 1. Okay, so the idea is, given a circuit that looks like this, we have to find the Thevenin's equivalent with respect to terminals A and B. Okay, with respect to terminals A and B. And there are 2 ways we can do it. The first way is to solve for open circuit voltage. Okay, we'll do that technique, and then solve for Thevenin resistance. So there are 2 steps that we have to do. We have to solve for open circuit voltage, and then the next step is to solve for Thevenin's resistance, RTH. Okay, VTH. Okay, so that's the idea. Okay, so let's see if we can do this, if we can solve this. I'm going to, let me make this a bit less colorful. Okay, this is all. Okay, problem number 1. Okay, so what we are going to do is to, let me run through the steps one time, and then I let you work on the next problem yourself. So I'm going to call this as VThevenin. Okay, so that makes this voltage at the node over there equals to VThevenin. Okay, I'm interested in calculating the open circuit voltage when the terminals A and B are open circuited. Okay, if I were calculating the Norton equivalent, I would short these two and look at the current flowing in here. Okay, Norton current. Here I'm interested in calculating the Thevenin voltage. Okay, Thevenin voltage. Let's see if we can. The next step, the first step here is to, for A, Thevenin's voltage, that is VTH. Okay, in order to calculate that, I call this node to be VTH. Okay, that node to be the open circuit voltage to be VTH, and that makes the node over there equals to VTH. Another thing I'm going to do is to call this node as V1. Okay, I'll call this node as V1 as it is my practice to name all the nodes. Okay, I can call another node as well. I can name this node to be, I don't know, I can call it V2. Okay, but as you will see, V2 is at 9 volts. You see, there's a positive 9 volts over there. Okay, so V2 is really at 9 volts. So in order to calculate, in order to do the VThevenin, in order to find the VThevenin, I'm going to employ node voltage method. Okay, so I'm going to employ the node voltage method. Node voltage method. And for the node voltage method, I start by writing KCL at different nodes. Let me start by writing the KCL at node V1. Okay, so that's the node right here, node V1. Okay, who can tell me the KCL at node V1?
Is it going to be a negative direction through? I just want to clarify the direction first, the signage for V1 there.
Okay, so for V1, when it comes to node analysis, I assume this is at a positive voltage. So the idea is I add all the currents that are leaving the node. Okay, so here I'm not going to pay too much attention to the signage. I assume that all the currents are leaving the node and it will lead me to a consistent solution later. So I'm going to assume that V1 is at a higher potential, positive, and all other nodes are negative with respect to V1 at this particular step, at this particular, when I'm doing just this step. Okay.
Okay, that makes sense. Thank you.
Okay. So anybody wants to give me the KCL at node V1?
Is it V1 minus V2 over 5?
V1 minus V2, which is 9 volts over 5. Yes, plus
V1 over 25.
plus V1 over 25, correct?
And the current source is kind of throwing me off. Is it?
It's just the value that I can directly pick there, 1.8 amperes.
Okay, so I don't. You just add the 1.8. You don't have to worry about the voltage.
Correct, correct.
Okay.
Correct. Okay. So all of that is going to be 0. So this is equation 1, KCL at node 1. So let's do another KCL at node this guy. Okay, so let me pick node VTH and do KCL at node VTH. That's this guy. Okay, so in this case, in the case of KCL at node VTH, I assume again that all the currents are leaving. So when I account for this current source, I'm going to have to put a negative 1.8 in this direction, which is exactly same as a positive 1.8 in this direction. Okay, but to be consistent with my process, I'm going to consider all the currents as leaving. There are 3 currents leaving in 3 different branches. Okay, when it comes to KCL at node VTH. Okay, so anybody wants to give me the expression for that?
So this time, I'm trying to make sure I'm getting this right. Is it going to be the VTH minus V1 over?
VTH minus V1 over.
And then do you go over the, but there is no resistance here that they're going across. So can we ignore?
Are you talking about this guy?
Yeah, since that one is just the current there.
For the current source, I don't have to calculate the current source value. I already have it to be 1.8 amperes, right?
Exactly. So we don't need to worry about going across any resistance from VTH to V1, right?
Correct, correct.
Oh,
If you think about it, all of this is simply the current. Voltage over resistance is the current. But fortunately, I have that number already here. But the direction that I picked is opposite to the actual direction of the current. So I'm going to account for that disparity
with the
using,
negative. Okay.
yes, yes, sir. I'm going to account for that disparity using a negative sign, okay, 1.8 negative, okay. So I don't have to worry about the potential difference through that branch, okay.
Then what about, would we do VTH minus V2 over 20 ohms? Is that right?
VTH minus V2, correct, which is 9 volts over 20 ohms, correct.
Okay.
And what else? If I call this the ground, there is one more branch.
And then is it just going down in the VTH? Oh, how do you account for ground though in the equation?
Is 0. Ground is assumed to be at 0 volts.
Okay, that's
VTH
easy enough.
minus 0, yeah, VTH minus 0 over 60 ohms, right?
Correct.
So
Yes.
all of this gives me 0. That's the node voltage, node KCL, Kirchhoff's current law at node VTH. Okay, questions about that? Now it's a matter of massaging these equations left and right. And then when you solve for value VTH, okay, it seems there are 2 unknowns here. Let's see, let's identify the unknowns here. There are 2 unknowns. There is V1 is an unknown and VTH is an unknown. Okay, so in order to solve for these 2 unknowns, I have 2 equations. Okay, 2 equations, 2 unknowns. Then I should have have a value for V1 and VTH. Okay, so when I solve for that, the value for VTH I get is 30 volts. Okay, it's 30 volts. So this is my first step. This is what I was after, to find out VTH, right? So it's just a matter of solving 2 equations. And
Professor, how did you get
yes,
VTH equals 30 again?
VTH equals to 30 again. So it's just massaging this equation. Okay.
Oh, it's basically making it all equal each other in a way.
Yeah.
Okay, perfect. Thank
Yeah.
you.
Solving for VTH from this one equation number 2.
Got it. Thank you.
Okay. Other questions, please. All right. So Let's see. So when we do that, that's going to come out to be, oops, something's wrong here. Okay, something's wrong here. So here is the idea. Excuse me for that. I'm going to call this as V1. Okay, did a teeny tiny, this is V1, right? This is V1. So something I may have missed here is that this, all of this is supposed to be not VTH, but V1. Okay, V1 minus 9 volts, and this is going to be V1 minus. So for some reason, I kept forgetting this 10 ohms resistance. So the only thing that's changing is that VTH is not equals to V1. So in this case, V1, if I solve for V1, V1 is going to come out to be 35 volts. Okay, V1 is going to come out to be 35 volts. And when I solve for VTH, okay, when I solve for VTH, which is the voltage division between 60 and 10 ohms, then I'll get VTH to be 30 volts. Okay, so the only change to this problem that I have done so far is noticing the fact that this is not VTH. This guy is not VTH, but it is V1. Okay, owing to the fact that there's a resistance here. Okay, but the rest of the analysis all remains the same. Okay, so let's see if we can find the Thevenin equivalent here. Okay, Thevenin equivalent resistance. This is, I'm going to copy this. Okay, and then add a page. So far, all I have done is to calculate the Thevenin voltage, V Thevenin open circuit voltage. Right now, I'm going to do the Thevenin resistance. Okay, let me show you how I do that. So the first step is to find the open circuit voltage. We did that.
Hey,
We found
Professor,
this guy to be, yes.
on the previous example that we're just doing, and then the other
Yes.
V1, would that just be like V naught or some other type of V?
Yeah, thank you about that. So we can call this V naught, just so there is no conflict. So I'm going to call this as V naught.
Okay,
All
thank
of
you.
this is, thank you. That's a good observation. Okay. So now let's see if we can solve for the, let's see, crop this, Thevenin equivalent resistance. Okay, Thevenin equivalent resistance. Okay. In order to find, so that first step was to find VTH. We found VTH to be 30 volts. The second step is to find RTH. Okay, in order to find the RTH, what we do is to deactivate all independent sources. Okay, we deactivate all independent sources. So there are two independent sources here. There is one voltage source, there's one current source. Okay, so in order to deactivate them, all we have to do is to replace the voltage source with a short, okay, and the current source with an open circuit. So this is what is going to happen. I'm going to have the 5 ohm resistance as is, okay, the 25 ohm resistance like so, but I'm going to replace the current source with an open circuit. Okay, then there is a 60 ohm resistance over here. Okay, 60 ohms. Then there is a 20 ohm resistance like so. Okay, and then the voltage source, this guy, I'm going to deactivate it by short circuiting it. Okay, by short circuiting the voltage source. Does that make sense? So all I have done is to, and let me not forget, for some reason I keep forgetting the 10 ohm resistance down below. Okay, Yeah, this time, let me not forget that. Okay, so 10 ohm resistance down below. So all I have done is open circuited the current source, okay, and short circuited the voltage source. The voltage source has been replaced by an equivalent short, and everything else is exactly the same in this circuit. So I'm going to get rid of these two extra wires that are not doing anything, that are not conducting current at all. So here is the idea. So there is a resistance of, and then I'm interested in calculating the resistance looking into this, Rn, right? Those are the two terminals and across the 60 ohm resistance, Okay, so everybody with me so far? All I have done is short circuited the voltage and open circuited the current. Now take a look at these two terminals, terminal X and terminal Y. Okay, what is very interesting about these?
They're series.
They're in series. You're talking about these two resistances, right?
Yeah.
Those two resistances are in series. But what about this wire over here? So you're right there in series. So I can write the equivalent of them to be 30 ohms.
Well, won't the current want to go through the wire with no resistance over the wire
Yes,
with
yes,
resistors?
correct. So if I have a short circuit in parallel to any resistance, then the equivalent resistance is going to be 0. So this is a 0 ohm resistance. So in other words, this is all going to go away from my circuit because it has been shorted, right? So the idea is it's all of this circuit is going to transform into 20 ohms, okay? And this part of the circuit is going to go away because it has been shorted with the 0 ohms in parallel. So that's going to be replaced by 0 ohms, followed by the 10 ohms right here. Okay, that's the 10 ohms right there. Okay, and then of course there is a 60 ohm resistance across which I want to find out the Rn. Okay, so I have 20 in series with 10. So in effect, what I have is a voltage, a 30 ohm resistance in parallel with a 60 ohm resistance, and that's the resistance looking in to the circuit. Does that make sense? Okay, so the equivalent of 20 in parallel with 60 in parallel with 30 is going to be 20 ohms. So these are the two steps. This is R Thevenin. R Thevenin, therefore, is 20 ohms, and V Thevenin was 30 volts. Okay, so the argument would be that all of the circuit above, okay, that would be exactly identical to one voltage source with 30 volts and a 20 ohm resistance in series. So this is VTH. This guy is RTH. Okay, does that make sense? Questions, please.
So is this generally used on like really large circuits where you can kind of take a portion of it and simplify it?
Yes, yes. Also, if you have a black box kind of circuit, okay? And you're trying to connect a load to it, okay? And you want to match the impedance of this guy, the internal impedance, to this guy. So you have to have a way of expressing large circuits in the form of a Thevenin's equivalent, just so it's easy for you for further analysis. So you're right. So it's used to simplify large portions of the circuit into simple representation that behaves exactly the same at these terminals A and B.
Thank you.
Okay. Other questions, please. All right. So I'm going to give you a little bit of a task. Okay. Let's see. Let me copy this again. Copy this and go here. Add a page. So we're going to look at the exact same problem again. But slightly differently, okay? So what we are going to do is, so far, what we did was to find the Thevenin, right? Open circuit voltage, okay? Thevenin. What we did was to open circuit these two terminals and find the voltage across that. Now what I want you to do is to find the short circuit current. Short circuit this terminal and find the current I Norton going through this, okay? Using the exact analysis techniques, okay? Using the exact analysis techniques, okay? So instead of finding VTH, now your task is to find I Norton. So instead of finding the open circuit voltage, you would use a node voltage and node current method to solve it using Norton current, short circuit current. Okay, what is the short circuit current? Take about 5 minutes to work on that problem. All right, so I'm going to, what value did you guys get for I Norton? You should see an answer of 1.5 amperes. Okay, you should see an answer of 1.5 amperes. And why don't I do this problem myself? Okay, why don't I work on this myself? And let me identify the nodes here. I'm going to call this node V1, okay, and call this node V2, okay. Call these two nodes V1 and V2. Okay, so the first thing I'm going to do is to write the KCL at node V2. Okay, KCL at node V2. Let me park this somewhere here. So KCL at node V2. Okay, at node V2, the first thing we want to recognize is that this guy, okay, this guy is not present in the circuit anymore, because it is short circuited with a parallel 0 ohms path, right? So questions about that, the first thing I'm going to do is to remove this part from the circuit. Okay, that's because I short circuited using a parallel path just to the right of it. Okay, so then the current flowing in this branch would be, okay, that would be, let's say V2 minus 0 over 10 ohms. Okay, so that's the current flowing in here. Okay, and then I can look at the current leaving the node over there, which is negative 1.8 amperes. Okay, then the current leaving this branch would be V2 minus this voltage, which is negative, which is 9 volts, V2 minus 9 volts over 20 ohms. That is 0. Okay, everybody with me so far?
Yes.
Okay, so what value, it would give me a value of V2 equals to 15 volts. Okay, I have a value of V2 to be 15 volts in here. Once I have V2, okay, once I have V2, okay, that value, once I have V2, I should be able to find the current I Norton flowing in here. That guy is simply V2 over 10. Okay, that's the current leaving in there. I Norton equals to V2 over 10 ohms. That gives me 1.5 amperes. Does that make sense? Okay, 1.5 amperes. Okay, Sean, correct. So I'm going to show you something interesting. Okay, so the R Thevenin is still the same value that we calculated earlier. Okay, the R Thevenin value is 20 ohms as we calculated earlier. Okay, now my argument is this circuit can be exactly identical to a current source of 1.5 amperes. Okay, with a parallel resistance of 20 ohms. Okay, this is the Norton equivalent circuit. Okay, let's compare the Norton equivalent. Okay, copy that. I'm going to paste it over here. Okay, that's the Norton equivalent I got in the second part of the solution. Let me compare that to the Thevenin's equivalent that I got from my earlier problem. From the earlier solution, I had Thevenin's equivalent to be, copy that. Okay, I want you guys to look, take a closer look at both of these. Okay, and see if you can make an observation about those. One is the Thevenin's equivalent. For the circuit, okay, and the other is the Norton's equivalent for the exact same circuit.
Their source transformations.
They're source transformations of each other. So if I were to take this voltage source here and transform it to a current source, then the current would be 30 volts by 20 ohms in parallel with 20 ohms, which is exactly the same as the Norton's equivalent. So the Thevenin's equivalent and Norton's equivalent are the source transformation of one another. Okay, So let me go back a minute to the step of Thevenin's equivalent, because it seems there was a question about that. So Thevenin's equivalent, when I was calculating that, I called one of the voltages as V0, right? Sorry about that. Sorry about changing the names on you, okay? I called this node as V0, okay? The voltage at that node, I called it to be V0, and the voltage between A and B to be VTH, okay? So V0 and VTH. The idea was, in order to find VTH, all I did was to do a voltage division between the 60 ohms and the 30 ohms. Okay, I did a voltage division between the 60 ohms and the 30 ohms. That's how I got the value of VTH equals to the voltage division between 60 ohms, 60 by 60 plus 30 into VO. Okay. Why do I keep saying 30? 60 plus 10. This guy, sorry, 60 and 10. Okay. So 60 plus 10 times V naught. So how did I get VTH from V naught? Simply by applying a voltage division. Okay. Does that make sense? Okay. So this node, I renamed it a bunch of times and I called it V0. Because I kept forgetting this resistance over here. But at the end of the day, in order to get VTH from V naught, I simply apply a voltage division between 60 and 10. Okay, so that's the idea of Norton's equivalent. Finding the Norton's equivalent amounts to finding the short circuit current. Okay, let's see if we can do another problem. Okay, this time we'll do a problem with a dependent current source. Okay, let me see. I'll go here. This is problem 2. Let me copy this. Okay, so let me see if I can add a few pages here. Add a page. Add a page. Okay, so I'm going to properly name these pages. Okay, so this is problem number 1. In class problem 1. Okay, we'll do another problem. Problem number 2. Okay, this is problem. So in class problem. So give me a second. In class problem number 1. And then we'll go back to doing this. Okay. Okay. So the question is, how do we find the Thevenin's equivalent? Okay. How do we find the Thevenin equivalent of the circuit here? Okay. Now this guy. So the question is, find the Thevenin equivalent of the circuit with respect to terminals A and B. Okay. Now, if I call this as VThevenin, and I'm interested in finding VThevenin, and I'm interested in finding the RThevenin as well. So I will eventually get a value for VThevenin. and a value for R Thevenin. Okay, and I'm going to fill in those values, Thevenin's equivalent. Okay, now I can make the assumption that this guy is also VTH. Okay, if I think of this as a ground, if I had a resistance down here, then this would be a different value. Okay, then the voltage dropped across this will have to add to the voltage dropped across that to give me a node value for that guy. But because there is no resistance here, I can assume that this guy is also going to be V Thevenin. Okay, now what I can do is I can write KCL at node V Thevenin. Okay, when I look at the KCL at that node, there are 3 branches of currents flowing in there. There is 1, there is 2, there is 3, and so there's actually 4 branches of currents flowing in there. I can sum them all up. Okay, this is what I'm going to write. The equation V Thevenin minus 24 by 2 ohms. So that corresponds to the current flowing in that branch. Okay, and then there's a current flowing down below. So earlier, this current was corresponding to the current flowing in the left. Okay, current flowing in the left. Okay, then there is another current. Then there's a third branch of current, this guy. Okay, so let me write down the second one. The second branch of current is 4 amperes. See, I chose a direction of going down, and that aligns with the current source here. So I include a positive sign. Okay, then there is so that's the current right here. That's color coded in green. Now there's a current shown in the blue branch. So that's going to be 3 times Ix. Okay, 3 times Ix. That's the blue current over here. Plus there's a current flowing in this branch over here. Okay, which is going to be VTH minus 0 by 8 ohms. Okay, that all of that equals to 0, and this is the current flowing in the purple branch. Okay, so there are 4 different branch currents at that node VTH, the one shown in red, the one shown in green, blue, and purple, and I have accounted for all of those. Okay, so now there's a constraint equation. There's an equation there appears to be an unknown Ix. Okay, in order to account for Ix, what I can do is to simply write Ix to be, that's the current flowing in this branch, to be the voltage over there, VTH, minus the voltage over here, 0, over the resistance, 8 ohms. Okay, 2 equations, 2 unknowns, we can jolly well solve this problem and get an expression for, so this is going to be give me a value, this is going to be giving me a value of VTH equals to 8 volts. Okay,
Professor, sorry for interrupting you. For Ix, if you got VTH minus 0, where would the 0 be coming from exactly?
That's the reference ground.
Oh, the reference. Okay, the reference node. Okay, thank you.
Yes, yes, that's a good question. Other questions, please. That's a good question. All right, other questions. Okay, so now VTH comes out to be 4 volts, 8 volts, sorry. VTH comes out to be 8 volts. Okay, and VTH is 8 volts. Is that it? I found the value of VTH to be 8 volts. How do you find the value of RTH here? In order to find the RTH, okay, we have to apply a different technique, the technique that we discussed earlier. Okay, so let me see if I can add another page, clear this up. Okay, so in order to find, to just add another page here. Okay, so VTH has been found to be 8 volts. Okay, the next step is to find RTH for the same circuit. Okay, let's find the RTH for this circuit. I'm going to copy this and paste over here. Okay, okay, and let me see if I can okay, never mind. So in order to find the RTH, what I have to do is to do this technique. Remember I mentioned I have to apply a test voltage and a test current. Okay, V test, and look at the I test. And when I'm doing that, I want to deactivate all the independent sources. I'm going to deactivate that independent source by short circuiting a voltage source, and I deactivate the current source by open circuiting. Okay, these are the only two independent sources. I don't touch this guy. That's a current source, but it is not an independent current source. It's a dependent current source, so I don't modify it. Okay, so what I have to do when I'm doing a test voltage, test current method, so this is again RTH using V test, I test method. And I apply this when I have dependent sources. Okay, earlier in the last problem, I simply found out the RTH directly because I did not have